Hello, and welcome to New England Dynamics and Number Theory seminar. It's 12:15 in New England and some other times elsewhere because the daylight savings time has changed here, but not everywhere. Hopefully, people will join us later. And today I'm happy to see Shreyasi Datta from Uppsala. As I wrote in the introductory email, the title is very optimistic. We don't see that bed is null very often. Most of the times we look around and bed is everywhere, or almost everywhere. But now we have a statement that bed is null via constant invariance, and Shreyasi will tell us all about it. Welcome.
Thank you very much, Dimitri, for inviting me to talk. And thank you all for attending the talk. So I will talk about bed is null, and everything will be joint work with Victor Beresnevich, Anish Ghosh, and Ben Ward. Okay, so I'll first start with very basic setup. So let's start with everyone's favorite Dirichlet's theorem. So we know that for every vector x in Rn, so usually I'll write x and every coordinate of x is xi. So we know Dirichlet says that there are infinitely many integer vectors p and q, such that you can say that if you take 1 by q to the power 1 by n, then you will always get infinitely many such rationals near x. Okay, so this is a nice theorem that holds for every x. So naturally, question is what happens if you try to make the constant one go to 0. Okay, so that's where we have the definition of badly approximable vectors. So we say that x in Rn is badly approximable if you can find a constant c such that the same equation as before turns to opposite direction. The inequality turns in the opposite direction, and you have a constant c here, and it holds for every p and q. So you cannot improve beyond c for this kind of vectors. Okay, so then what do you expect to be the size of this set? Okay, now when I say size of this set, it doesn't make really much sense because you need to mention what with respect to what. Okay, so let's first start with the Lebesgue measure on Rn. So it's very well known that the Lebesgue measure of this badly approximable vectors is 0. So in the first few minutes, I will try to show you different ways to show that this set is Lebesgue measure 0. And I'm not saying that these are the only methods. There are other methods. Okay, so let's say first, so one can show that these badly approximable vectors are actually inside this set of Dirichlet improvable vectors. Okay, so what is Dirichlet improvable? So I only stated the Dirichlet corollary, but you actually have a more a stronger statement, which is where you have that for every x, if I replace this one c by 1, then you always have non-zero integer solutions for all q large enough. Okay, and Dirichlet improvable vectors are those for which you can improve the original Dirichlet's theorem by this constant 1. I mean, you can replace the constant 1 by some smaller constant c. And although it's very surprising, but it turns out that badly approximable vectors are inside these Dirichlet improvable vectors. And it's known that the Dirichlet improvable vectors are also a Lebesgue measure 0. And these were arguments by Davenport and Smith. So, okay, so this is one. Okay, then there is another way of saying that the badly approximable vectors are of measure 0 with respect to Lebesgue. If you look at much stronger result, okay, so let's say you start with an approximating function psi, which is monotonically decreasing, and you know Khinchin type results. So what is Khinchin type result? So let's look at this W psi, which is such that you can approximate with this error rate psi of Q infinitely often. And then you want to know what is the size of this set. So if you look at the size with respect to Lebesgue measure, it turns out that it depends on how psi behaves. So if the summation of psi to the power n diverges, then you know that this set is full, which means that the complement is Lebesgue measure 0. So for instance, in the Dirichlet's theorem, we had psi to be 1 by q to the power 1 by n. Okay, so now this tells us that the badly approximable set has measure 0 because one can see easily that this is inside this W complement. So this is the function psi. And Khinchin type result, especially the divergence part, tells you that this has measure 0. Okay, but this both the first and the second are much stronger results, as you can see. And then also there is a dynamical proof of the fact that of the same fact. So how it starts? So let's say you want to work with X in Rn. You can embed X inside G mod gamma as this unipotent lattice, where G is SLN plus 1R and SLN gamma is SLN plus 1Z. And there is a correspondence between how one can translate problems in Diophantine approximation in homogeneous dynamics. So it turns out that if X is badly approximable, then if you look at if you look at this point and if you act by the diagonal action GT, then this orbit must be bounded. So if X is bad, if and only if this orbit is bounded. Okay, now we know that the GT action on this space is ergodic. So therefore, we know that if you take the Haar measure on G mod gamma, then the bounded orbits are of measure 0. And then from there, you can just work a little and actually show that you can get down one dimension or much dimension less, and you can actually conclude that even if when this lambdas are of this form ux zn plus 1, then also the Lebesgue measure is 0. Okay, so here you need to have a measure that is invariant under the action that you are talking about. And also you have to get down to this kind of from upper dimension to a lower dimension. Okay. So these are 3 methods. And it seems like in all of them, we are trying to prove. So if you want to just know whether what is bad, the size of bad with respect to some measure, seems like these 3 methods are actually showing much stronger result. It is showing much stronger result. So let us look at another method. Okay, so here we are considering the functions which are of this form. So so in the previous case where we were talking about hinging type of result, we were looking at like 1 by q log q or 1 by n. But instead, let's say we look at c by q to the power 1 by n. And we know that just by the definition that bad is inside the complement of such sets. So if we know that these sets are of same Lebesgue measure, and we know Dirichlet theorem, which tells us that if C is 1, then this is everything. So that means if I know that, okay, by changing the constant, the size of the set doesn't change, that means it's actually 1 together with the Dirichlet theorem that is full. So therefore, this has measure 0 and then bad has measure 0. Okay, so this is what I generally will refer as constant invariance. So always it's with respect to some function. And we will mostly talk about functions that are of this Dirichlet type, which means that like these functions.
Okay, so can I ask you something about
Yes.
this? So first of all, is it true that you have actually equality of the sets? You wrote that bad is inside, but I think it's
yeah, it's actually
the definition is just that it's equality. Okay, that's fine. It doesn't matter. But just out of curiosity, so whose theorem is this? Who proved that using method 4? So part I. Is it Castles or is it somebody else? Just curious historical reasons.
So I don't know if it appears somewhere as this, but if you just talk about, so there are two things. So there is this kind of results where
Yes, that's what I meant.
I think that was dealt with by Castles. And there is also a result where you have to show 0-1 law. So if you instead of this, if you work with some function psi, then you should have 0-1 law and also this constant invariance.
So this is Castles.
Yes.
Okay. And another historical question, out of these 4 methods, so who actually proved this result first? When was it proved that the approximate vectors have measure 0?
Right. So
which is the oldest one? Is it by Hinchen?
I'm not 100% sure. It could be by Hinchen because Hinchen theorem was proved in 1926.
26,
right?
yes.
Yeah, so I would assume that he proved it.
Yes, but this the case of badly approximable numbers is easier, right? Because its a function is easier. So
yeah, right.
So for example, in one dimension, I think it was known by continued fractions even before Hinchen. So I just thought maybe you know today. Okay, never mind. Okay, let's continue.
Okay, all right. So so this is kind of the general philosophy that I wanted to start with, and now maybe I can start writing. And please feel to interrupt and ask if you have any question. Okay. So let me first start with more general bad sets that people are interested in, which is weighted badly approximable vectors. So what do I mean by weight? So let's say you take a vector W, which is in Rn. So we call that this is on weight if summation. So first of all, this is all of them are greater than or equal to 0, and summation of Wi is 1. Okay, and then you can call this a bad of W such that maximum of Qxi minus Pi 1 by Wi is greater than C by Q for all Q and P. So there exists. So we say that X is in bad W if and only if there exists a constant that may depend on X such that this reverse inequality holds. So now I just wanted to mention that if you take all the weights to be same, like Wi's are all 1 by n, then you are back to the previous definition. So the difference is that here we are allowing the coordinates to grow in different rates. And this is not a norm, but this is a semi-norm. Okay, and now I can just go back and ask the same kind of questions. Okay, what methods 1, method 2, and so on does. So it starts to become more complicated. So for instance, I should mention that, like, let's go back to the method 1. So if I had to, let's say, replace this is no longer that, I mean, this is a theorem by Kleinbach and Rao. And also the second one, if I replace by W, this is a theorem by Kleinbach and Weiss. Okay, also, I think theorem method 2 will still be more classical so in this case, what you have to do is that instead of one function that approximates all the coordinates, you have to take Psi1, Psi2 up to Psi n. And then the condition here would be that product of Psi n should diverge if in order to say that the complement of such is measure 0. I think that was known before the, long time back.
Well, it's probably Schmidt's theorem. Follow some Schmidt's paper, 1960 or something.
Okay, and then method 3 can be actually applied almost as the same in the previous case. The only changes would be that here you will take with weight. And then, okay, so the way so it will be this diagonal flow, and everything will be unchanged as before.
Well, this a little work will be much more.
Yeah, little work would be much more. Yes.
Actually, I don't think you can use ergodicity. It's actually more in, because from this implication will be hard to implement. You actually need to talk about equidistribution of this weights.
Yes. Yeah, right. Because here somehow I don't want to too much into it, but the thing is that here the way to go from this statement to this statement is that you write lambda as like some other matrix times ux times that, and then you
maybe other way around. Yes.
Yeah, other way around, and then you show that if you take gt of lambda, then gt of this ux, and then you conjugate. So then gt inverse gt, and then this part is somehow bounded. But if you take different weights, then it would be a problem. Okay, all right. So let me start with the main thing of my talk, which is that, okay, so I talked about all these methods. Now, what is the question that we want to study? So the question is, let's say we want to replace this lambda n, the Lebesgue measure, by some other measure. And here I will choose the measure to be f star of lambda d, where f is a map from some open set of Rd to Rn. And let's say it's a continuous map. And the question is that, okay, what happens f star of lambda d of that W? So this is the main question that, this is one of the main questions that we will be interested in. Okay, so let us just see what is this measure. So first of all, this you can see that this f star lambda d is a measure on Rn, and I can write down this set as, so this above set is just nothing but all x in U such that f of x is in bad W. Okay, so all right. So now let's see what are the previous results. And okay, before I proceed, you can also replace lambda n by any Borel probability measure and ask the question. Okay, so previous theorems. And as I mentioned, like in the classical setting, there are many ways, like there are 4 ways that I said one can try to prove these kind of results. So here in case of manifolds, like in case of this push forward measures, also there are stronger results that will imply in some cases that the same result holds. So let me try to say what are the conditions on F. So let's say F is non-degenerate, which I'll not explain, but in case of analytic maps, it just means that, so let's say in case of analytic, it just means that image of F is not contained inside any affine hyperplane. Okay. So then it was known that f star of lambda d of bad n is 0. So that is like the unweighted case, where all the unweighted case means all the weights are same, which is that this one. And
so whose theorem is it? Is it
yeah,
our paper with Victor, or was it known earlier in this case?
okay, so let me go by method. So method 1, which is that, so there, I mean, many papers, I don't know which one is the first to imply. So definitely your work with Beresnevich, Barnik, and Margulis imply this.
But this is method
Method 2. Yeah. So method 1 is by Nimisha and also, I mean, many papers of Nimisha and also with his student Peng Yang. They consider these kind of functions, but they always have analyticity. And in some cases, they also consider functions that are not non-degenerate, but they have some conditions. They have some restrictions on the function, and they show that the Dirichlet improbable vectors under this measure f star lambda is 0, so it implies. Okay, and then method 2 is by many. I mean, it follows. So maybe I'll start by this one: Beresnevich, Barnik, Feinberg, and Margulis. Also by Beresnevich, and also by Beresnevich, Dickinson, and Bellani, and plus many. And I should have, but I did not check which one. I mean, I know that this one is from 2002, and this is 2012, and I think this is around 2007. But I'm not 100% sure if this can be done from results even before that. Maybe in some cases it was done. I think for moment curves,
I think for the parabola in R2, for example, it was proved by Bernik.
Yes.
Very long time ago.
Yes, right. Okay. So I will not talk about method 3 because somehow in method 1 itself, Shah uses effective equidistribution. So I'll just
not effective, ineffective.
Not effective. But I think in case of curves in R2, there is a recent work by Lay that he talked about recently, where he actually proved effective. Okay, all right. So now let's talk about method 4, and also one of the results of this talk. So this is a work. I mean, this is a theorem by okay. So again, let me just recall that, okay, F was some map from Rd to Rn. And let's say M is n minus d. Okay, and so our first thing is that if F is C2, and I just assume, so we just assume that F is a C2 map, then the first conclusion is that F in F star lambda d of bad n, which is again the unweighted, is 0. So the main new examples in this part A is the line or flat ones that were not considered before, and especially the ones that are not analytic. And then the second one is more, I mean, I think that is the main thing that I wanted to say. So let's say W is not the unweighted case, which means it's not the standard weight. Then we have a mild assumption, which is that also together with C2, that almost everywhere the tangent plane is not perpendicular to any coordinate. Then we have that F star of lambda d. Oh, this is 0. Okay, now I want to talk a little about this condition on X, that the tangent is not perpendicular to any coordinate. So I can just actually replace this condition by this one, which is that so you are starting with this weight, and if you don't have, like, if you have this condition that almost every point the tangent is not perpendicular to any of the axes, then you can use implicit function theorem, and then or inverse function theorem, and then you can show that you can somehow reparameterize. So we are talking about the image of U, right? But you can reparameterize such that the maximal weights are in the d many coordinates, in the first d many coordinates, and then you have that I equal to 1 to d is greater than maximum wd plus j equal to 1 to m. So all your, like, the first maximum weights are in your first d many coordinates, and we are parameterizing such that the f of x is just x comma f1 of x. Let me write f d plus 1 of x up to f of n of x. So this x is d many coordinates, and then I'm starting to have these functions. Okay. So let's say this is theorem A. Okay, any question before I maybe move on?
Sorry, I'm confused about the last remark. The tangent plane is not orthogonal. Tangent plane is not orthogonal to any coordinate. This is a condition on F.
This is a condition on F.
But what you wrote in green is condition on the weights.
Right. So what I'm saying is that, so you can have this condition and write down the theorem. So I actually so let's say you start with a manifold M, and which is C2, and you have this condition, let's say called star, then you don't need to put any condition on the weight, and you can just say that, okay, M intersection bad is 0. Null, right?
Okay.
But if you don't want to do that, I mean, we know that it's enough to prove it.
I see. So without this, so you're saying, so for example, if your M is the x-axis in R2, then you are saying that the result is actually false, right?
Yes, then if it is the x-axis, then you know that. What do you know? Then
for some choices of weights, you are not going to have.
Yeah, we are not saying that this theorem tells you anything.
Okay. No, not the theorem tells you, but actually the set of badly approximable vectors is the whole axis.
Yeah, exactly.
Is that what you are saying?
Yes.
Okay,
So
I have to check.
So no, I'm saying that so our theorem only deals with the ones that are not, like the tangents are not orthogonal to any of the axes. So in particular, if you take x-axis or anything that is parallel to x-axis, we cannot apply our theorem directly. But if you take the lines, I mean, so then it depends on where it is passing through to say that whether it is, it has that the bad is full or.
I understand. I'm just saying that for the x-axis, you can actually say more because you know how to approximate points on the x-axis.
Yes.
And you know the correct exponent. And so if your exponent is, say, off a little bit, then you know that you actually cannot approximate.
Yes.
Probably, right? I mean, maybe. Okay, maybe I'm wrong, but probably there are reasons why you need this restriction. Anyway, you can go on.
Okay, all right. So I should also mention that, and I think it will be clear when I start talking about somehow the proof. So we also actually do this over local fields QP. So if you take the same setup as before, only you replace that this is map from QPD to QPN. Then you have the same statement as before. So this is 1, and then 2. If you have, if you in fact want to generalize more from QSD to QSN, where QS is just QP, let's say QP1 plus QP2, or more products, then we need more restriction than it is C2, and in fact you need that F is extremal for every weight. Then you have the conclusion. And there are some technical reasons why this condition is appearing for more arithmetic setup. Okay, there are other things that I want to talk about, but before that, let me start with how one can try to prove these theorems. And behind this theorem, there is an abstract theorem, which I'll not attempt to write in its full generality, but I'll just write the one that I need for these theorems. Okay. So let's call this abstract theorem. And this is inspired by works of Castles and then further developments on it. Okay. So let's say you take R D and you take the measures mu I on each R. So you're just talking about this measure mu on RD. You have a function phi, P1 up to Pn, where each Phi is a map from R to R plus. Okay, then I should mention that also have the condition that phi of q goes to 0 as q goes to infinity. And so far, I was talking about approximations where you were allowed to take all rational vectors, like you were approximating by all rational vectors. Now, what I'm saying in this approximation that, okay, let's R be a sequence of rationals in RT. So if mu has doubling property and this R is inside the support of mu, if this is the condition, then this implies that mu of WR, I'll define what this is. P is same as mu of WR of CP for every C greater than 0. And what are this WR phi? I mean, we talked about approximations before with respect to some function. Here I'm just talking about limsup sets of balls, but they are with the limsup is running over this curly R. So let me just define what this R, this set is. So this is just limsup over R of X in RD, and this is just a ball. So just write. I have a reason why I'm writing this way. So I equal to 1 to D. So this is essentially nothing but this set here is nothing but just a ball with radius phi q, and I'm saying that the radius should go to 0 as q tends to infinity, and you are, instead of taking over everything, you are restricting over some R. And if mu has this doubling property, and if the approximating, like the sequence of rationals that you are considering is inside the support of mu, then you can say that these two sets are of same measure, mu. Okay, I should probably mention very briefly what doubling means. So it just means that if you take a ball of radius r, then if you take 2 times the ball, the measure of that should be less than some constant that doesn't depend on the radius of the ball times mu of b. Okay, so now we have this abstract theorem which tells us how these limsup sets are of same size. But now we have to be able to actually use it in our setup.
But this theorem is due to Castles when R is all the rationals and when mu is Lebesgue measure, right?
Yes, yes.
Okay, and if you, when you prove this theorem, you're basically doing the same as Castles, or there are some difficulties?
It's basically same as Castles, and also we dealt with more generally. So instead of this being just a sequence of rationals, you can take sequence of sets, and also this being just limsup sets of ball, you can take more like rectangles.
Well, these are already rectangles because the functions are different.
These are already rectangles, right? But yeah, you can actually take R to be a set instead of a point.
What do you mean? Sorry. Oh, I understand.
R, yeah, this curly R you can take to be, like, for instance, if you want to consider Dartner approximation matrices, then you have...
Sure. But also, how important for this R to be a subset of rationals? Probably it's not important.
Yeah, it's not important. It's not important.
And
I just wrote it. If
so
I
you can,
don't, yeah, I had to write with more indices if I don't want to write this. So I I just chose to write in this manner.
Yeah, but so you can take any countable set,
Yes.
and then you need some height, notion of the height.
Yes.
So you're saying for any choice of the set and for any choice of the height function, this constant invariance works.
Yes.
Okay, that's great.
Okay, now let me talk about, so I'll not talk about the proof of this. It's very topological, and so I will rather talk about how one can apply this abstract theorem to prove the theorem that I mentioned in the previous page.
Yes.
Okay, and why we cannot directly use it, because here you can see that, this set that we are considering, these are sets in Rn, and obviously this is a measure in Rn, but there is a dependency on the coordinates, which is why this is complicated to compute. And in fact, the previous works of that started with this Kleinberg-Margulis's famous work is, to deal with these, like how to measure limsup sets where you have dependency on coordinates. Okay, so somehow we want to avoid that, right? So we cannot directly apply f star lambda d and put it in this theorem directly. Okay, so let's see. So okay, idea of proof of theorem A, which was about real manifold. Okay, all right. So goal. What is our goal? Our goal is that we want to show that f star lambda d of W C. C is a positive number and C prime is also a positive number. And I'll just write this for now as, so this is a function that we were dealing with. No, sorry. Okay. So I wrote this manner, means that the first coordinate is approximated with this rate, and so on. And we want to show that this is same as f star lambda d of the same thing, same limsup set, but here I change it to C prime. Okay. Okay. And remember that we have this condition, sorry, not mind, that minimum of Wi equal to 1 to d is greater than maximum of Wd plus j. Okay, so the step one.
Sorry, but this is only needed when you have.
We have different weights. Yeah, this is needed. Otherwise this is anyway true, right?
No, I'm confused. If f is non-degenerate, you don't need it, right? That's what you said.
If f is non-degenerate, then you don't need it.
Okay.
But I think if f is non-degenerate, then there is no. I don't know, but all these results that I mentioned before, let's go back. These were all about the unweighted case. So one need to prove.
Okay. So what is theorem A again?
Theorem A. Okay. Theorem A is this one. That if you have
okay.
Yeah.
All right. Now I remember. but you have two parts, A and B.
Two parts, but like.
Okay, now I see it. So A actually follows from B.
Yes, exactly.
Because for the uniform thing, it's of course true.
Yes.
Okay.
Yeah.
Okay. Sorry. Now I got it.
Okay. Now note that this set, let me call this, let's say star of C. So the star of C, so this is step 1. So star of C is nothing but lambda D. So it is x star lambda D of something, but I'm just going to write the definition of push forward measure, nothing else. So I have the, we are dealing with points such that you have x and then you start from fd plus 1x up to fn of x. Okay, and then you are looking at all those points x in Rt, or maybe actually x in U, such that xi minus pi by q is less than c by, so I just divided by q on both sides. Earlier we had q to the power w1, but I just divided by q, so I should have a q here. So these should hold for first d many coordinates. And then for the rest, I have, so d plus j of x minus, this should be the other ones. Okay, and now we want to somehow apply the abstract theorem, right? Now in the abstract theorem, we were allowed to take the approximation over some r, curly r, and here somehow the problem is that I have this approximations in the second part, but we are approximating for every rational vectors, right? So the plan is that if we can somehow make this second inequality vanish, then we can just rely on some rely on the abstract theorem and try to apply that, right? So if I want to make this vanish, then I should have more restriction on the rationals, rational vectors that I'm applying by. So what do I mean by that? So one can show by using Minkowski's convex body theorem, plus that the function is C2. So basically what you do is that you first apply Minkowski's convex body theorem so you just, I'm not writing everything, let me use this. Yeah, so you are applying on, so q xi minus pi, then you take q f d plus j x minus, you subtract the tangent part, some sense, so del I f d plus j x q xi minus pi minus pt plus j, and then q. Okay, so just imagine that you are applying, so you can rewrite this as you can try to apply the Minkowski's convex body theorem in Rn plus 1. And so you have to have whatever on the right hand side such that the product is 1. So we will try to apply that for this function. And we will then use the fact that f is C2. And okay, so let me write down what we will have and then say how we get it. So proposition is that for every x in U and delta positive, there exists a constant C that depends on x such that there are infinitely many integer vectors, non-zero, such that xi minus pi by q is less than, so here is the thing, so it's cx and some delta inverse, so that is bad. You have delta is less than 1 and you have as before. And then in the second part, we are able to forget about the x part. So we can just replace this by P1Q up to P D of Q minus PD plus J by Q and less than delta by. Okay, so the thing is that now we have something like before, but here this part does not have any X. But since we use Minkowski on this system, obviously I cannot have for both very small the constants, because I know that in order to apply Minkowski and for unimodular lattice, you need to have a volume 1. So that is how this part becomes bad, but this part is as you want. Okay, so this is just the first step. And okay, so I should mention why do we need this weight condition? Because from this kind of statement, we want to get to this kind of statement. So since in the first coordinate, we are in some sense losing. So in order to win in the second coordinate, we should have this weight condition that will kind of save us when you apply the Taylor's formula. Okay, so now we have something. Now the second trick is that we can now define the set R, the curly R that I was talking about. Okay. Okay, any question before that? So let's say this is, yeah, any question?
Not really. So you're basically okay. Go on. I'll ask later.
Yeah. Okay. Okay. So now we call this. So we define this set R delta. So delta is greater than 0 to be all P and Q in Zn plus 1, such that first of all this P1 by Q up to PD by Q, that should be inside the open set. And then if D plus J of, so let's call this pi D of P by Q. So pi D of P by Q minus so I'm not writing the exponents carefully because you know what they are. Okay, so this is kind of the rational vectors that are near the manifold. Okay. Now the thing is that we know that if we take, so we'll have this delta and then here we have another delta. So the previous proposition said that, okay, for every x you can find, so let's go back. So for every x you can find something in the x direction. The constant could be worse, but in the second coordinate you get delta, right? So that means that if I write this set where let's say delta is to begin with fixed, and we take capital delta greater than 0. Okay, so the previous proposition just tells us that this is nothing but everything, right? Because for every x we could find some capital delta that is that could be very bad compared to the small delta, but you do get. So this is the previous proposition. Now that just means that lambda d of them are same. And the Astor theorem that we proved, okay, so I'll come to that. But before that, also note that we were dealing with some union of sets where as you increase capital delta, the sets are increasing, right? So this is just nothing but limit as delta goes to infinity, and then lambda d of r delta of, so this is 1. And now we can use our abstract theorem on this measure lambda d, which is in RD, and say that, okay, so then each of them must be also, since each of them are same and the limit is 1, then each of them must be 1. Okay. And then you have, you are pretty much done. Only thing you need to show is that the, so if these are 1, then you are just looking at the complement. So that should have measure 0. But I mean, there is simple, I mean, there is little bit work that we should do after this. But basically, this is kind of the proof in the real case. Now note that here we needed that this, so in order to apply this abstract theorem, let's go back. So we had that this ball that we are taking, the radius of the balls should go to 0, right? This is the condition. And okay, so we applied mu on our lambda d, which has doubling property, and the r is also inside the support. Because we are only taking rationals. I mean, the support is everything. Now, I wanted to mention that in the arithmetic case, we had more. So where is it? Here. So in the arithmetic case, we had more condition like this. The reason is that when we talk about, like, we do similar kind of thing, Minkowski's convex body theorem, but the problem is that we have somehow gone from this to, like, we divided by q, right? Now, if you are working on p-adic or arithmetic setup, then if you take the q out, then the q nu is always less than 1, right? So if you take it to the other side, this condition on the ball may not be satisfied. So if you are in QP, then you can somehow manage to control the p-adic norms of the integers. But if you are in arithmetic setup where you have more primes, then it becomes complicated, and that is why we need this extra condition. Okay. I also wanted to, so that was kind of the idea behind this proof of theorem A and theorem B. And I also wanted to mention, can I have maybe 5 more minutes?
Of course. Maybe we can stop for a little bit and ask if there are any questions.
Yeah, sure. Yes.
No questions. Okay, let's continue.
Okay, so I also wanted to talk about another application of this abstract theorem. So I did not talk about all the applications that we have in that paper, but I actually want to talk about another application that we wrote in a separate paper, and I'll just take like 5 minutes. So there is a very beautiful result of Kim from 2007, which is that, okay, if you take x to be an irrational number, and if you look at all theta in R, such that qx plus theta plus p is greater than c by q for all p and q, then the Lebesgue measure of this is 0. So if you are familiar with badly approximable vectors in the inhomogeneous, you may probably know that, okay, there are 2 ways that you can try to understand. So you can vary either theta or you can vary x. So here what I'm doing is that I'm fixing x and I'm varying the inhomogeneous part theta. Okay, so this is a very nice result. And then later on, Uri Shapira improved this result, and he, among many other things, I mean, so the paper that he had this result, he had more general theorems. But one of the things that he proved is that if you take, in more generally, if you take matrices, and this condition that we had, that X is irrational, you replace it by X being not singular. Sorry, so X is not singular. So if you know that actually the irrationals are only, the rationals are the only singular vector, so it kind of aligns with dimension 1, or dimension 1 aligns with the more matrix setup. Then the same thing in more generality. So here you would have ux plus theta plus p. So I think it should be n by m for all q and p. So this is 0. Okay, and we have using, so this method of Kim was using continued fraction, and Shapiro's method was more dynamical, and we use our approach, meaning we use the abstract theorem that I stated, and show that the weighted version of, so I will not write it down, but weighted version of alpha result. So we take weight on both sides, meaning we take weight on this part, also we take weight on the height part, and we prove this. Okay, I want to stop here, and thank you very much for your attention.
Okay, let's give Shreyasi a round of applause, maybe virtually, maybe not. Any quick questions? Or not so quick? So I have some more questions, but maybe we're already kind of over time, so maybe I'll ask you by email.
Okay.
Point. Yeah, I think it's a very good presentation. Maybe just a quick question. So what especially what interested me was that you don't. So you have a kind of divergence theorem on manifolds. And in this divergence theorem, you have a manifold, and you don't require analyticity. You don't require n derivatives. It's only 2 derivatives.
Yeah.
Right. So it seems to be something really something new.
Yeah. So that is the main, in some sense, one of the main point of our work, that we don't need any condition other than C2.
But it only works. It only works for badly approximable ones. Are there any other functions that you can use to prove divergence theorem, or maybe convergence theorem? Because nothing really. I don't know anything. If you say, if I have a curve in Rn, which has not enough derivatives to use non-degeneracy, I really don't know how to proceed, even for the extremality. I
think Victor and others have a theorem where they also only assume C2, and they show the dimension of some well approximable number, the lower bound on the dimension.
Yeah, okay, maybe some work like this was done.
Yeah,
anyway,
they have from 2017 or 18. There is a work by 4 authors.
Okay, other questions? All right, let's thank Shreyasi again.
And thank you everyone for listening so carefully.